Okay, we're going to talk about velocity boundary layers. Now, just a reminder, we talked about boundary layers when we had pieces of glass or any other surface. In other words, if I go across to this teacup again, there's a very, very thin layer of air on the surface which is helping to insulate the cup, to prevent heat from quickly being radiated or convected off the cup. So we talked about that when we were talking about glass and glass panes. When you've got moving fluids of any sort, you have a boundary layer for exactly the same reason. So if I've got a surface, any kind of surface, we have this boundary layer. It's going to vary in size, it depends on the situation. Now, if we've got fluids, remember, fluids can be liquids or gases. So if I've got fluids flowing over a surface, so here's our liquid moving along, and it's moving with an average speed of whatever. Remember that the length of an arrow is an indication of the speed. This is what we call a velocity vector. So it's moving along, and here's another surface. Where it touches the surface, it's going to be completely stationary, not moving at all. So obviously there's going to be a transition between moving along there, and then as you get closer to the surface, it's going to slow down until it actually stops at the surface. So we've got two kinds of boundary layers like this. We'll assume that this is a gas or a liquid, it doesn't matter. And the gas or liquid can be either laminar flow or turbulent flow. We've talked about these. So remember, if it's laminar flow, everything is nice and smooth, everything is travelling in a uniform way. If it's turbulent flow, it's going to be wiggling and wobbling, just like when you've got a faucet or a tap. And you've got a little thin stream of water coming out of it. As it speeds up, it goes from laminar to turbulent. Okay, so we've got two kinds of flow, and both of those are going to behave slightly differently when it comes to flowing over surfaces. If it's laminar flow, then we're going to get a situation, and remember, we're going to draw our vectors. So here's the contact point, completely stationary. So in actual fact, I didn't draw this very well, the flow itself is going to describe a parabolic shape. And if it's turbulent, the shape is going to be more like this. We define a distance from the surface. Got our average velocity, and when we have this distance, which is less than 1% of the average velocity, we call this the boundary layer. Likewise for turbulent flow, so this is turbulent and this is laminar. The shape is different. In other words, the average speed is maintained a lot more because there's a lot of mixing, and it's only when you get down quite close to the surface I'll put that up there as well. We have Now, we'll stop at that, but we'll come back to this later when we're talking about heat transfer and heat exchangers and things like that, because with turbulent flow you have much better mixing, and heat, for example, can get closer to the surface that you're trying to conduct heat through. So for things like heat exchangers, turbulent flow is generally going to be preferred to laminar flow. There's a lot of different effects though you can get with this. I mean, if you're a small microorganism growing here, it's going to be a lot easier perhaps than growing a pig, because you're not going to be moved away. So in biology, in fact, there's a lot of other things that can result from these velocity boundary layers.